system with an emergency escape framework for blind and visually impaired people.
So here's the outline for our project. I'm not going to go through every slide, of course, but we're going to be very brief with some of these slides. It is pretty long, it looks, so we just included a lot. We're going to get through it pretty fast and focus on the main things.
So this is our team. I'm Alicia, and I'm the team leader, as well as the hardware team.
Sorry about that. My name is Charlie, and I am the hardware lead.
Hello, my name is Kari, and I am the software lead.
And I'm Vito. I'm part of the software team.
So for the need of this project, we just wanted to emphasize that around 217 million people suffer from visual impairment, and around 36 million suffer from blindness. So just as a clarification, not all visually impaired people are necessarily blind. So for the fire safety, for those that are visually impaired or blind, it hasn't really improved over time. Many of the education that we've received has been mainly catered to us visually, capable of seeing, stop, drop, and roll, look for a fire exit and such. So therefore, the visually impaired and the blind are at a much greater risk of injury. They don't really have the capabilities that we do, so they necessarily rely on other senses such as sound, smell, and touch.
So what is the big picture, you may ask? Well, many of us know someone who may be blind or visually impaired, or even struggles with another disability that could stop them from exiting a burning building safely. This fear can make it very difficult for people with disabilities to live independently. We want to help provide these people with all of the information they'll need to know what they're dealing with and what their next steps will be. Knowing they'll have an exit strategy at a moment's notice will bring peace of mind to them and their loved ones. House fires, such as the one shown in this picture you see here, would not be as frightening if a system was available to keep the residents safe, and we would be able to prevent countless lives from being lost. Therefore, we've decided to create a system that will detect a fire, alert the resident, and guide them to safety.
So for our existing projects, we wanted to look up some other projects that had a similar composition as ours. For our first project that was actually completed by Dr. Elmanai and Dr. Wang, they did an alert system that for fire emergencies. It will alert the user and alert other people, either both the police and fire department and also some loved ones. And our project is a little bit different because ours is also going to include a guidance system. For the second project, this one was more for everyday use. It did have a nighttime development as well, and it was mainly a user-friendly smart glass device, but our device is going to be a little bit different because smart glasses are not as durable, and ours has to be very durable for these situations. And then the last one is the last project included both indoor and outdoor routing, but the problem with that was they didn't dive too deep into the object detection. Their main routing was focused on walls, and going upstairs and just the map of the floor. But we will also include the object detection, including stairs, including chairs, trash cans, and everyday objects inside a house. And for originality, we're specifically designing a fire emergency system, which will include fire detection and mapping and guidance. And this will be able to help millions of lives.
Yeah, so our project summary here, basically we have a combined approach of object, fire, and exit detections. And then we're going to have the guidance to the exit ultimately as our end goal. We're comparatively better than just a standard fire alarm system, which simply alerts a user with a sound. We're going to have guidance here. And yeah, it's just a summary. We need high reliability and accuracy for this device. It's potentially life-saving and used in very dire situations. So that's also very critical here.
So as mentioned before, so the project requirements for us, since the nature of this project includes improving safety, we did take a lot of weight in accuracy and reliability in all of our criteria and implementation. So here's our weighted in our selection process. And then this is our selection process in terms of the connectivity between all of our devices. We decided to go with Bluetooth mainly because of the low cost, low energy, and we thought that it would be easier to implement in terms of our criteria and our project. And then this is our pairwise for the choosing our device. It was between the application, wearable device, and the home assistant device. We thought that the wearable device would probably be more portable, more safe for the BVI individual to use and be able to navigate themselves out. Although many of us are glued to our phones nowadays, I feel like for a BVI individual, they most likely find more easier for them to have a wearable device that they'll just, have on them during the day throughout their home. And this is our project requirements in terms of the engineering marketing trade-off. So as displayed here are criteria, and the double arrow representing the strong positive correlation, and the double arrow pointing downwards, the strong negative correlation, and this is our criteria.
Here we have our objective tree, and so for our smart fire detection system, we separated it into 4 components. So there's the functional design, the fire detection, the door and window detection, and the navigation. For the functional design, for the 4 components of that, it's compact, easy to use, cost efficient, and battery life. And as you can see at the bottom for battery life for 0.16, it's the most heavily weighted of those 4 because we thought it would be very important to have enough battery life to last through the night. For the fire detection, for accuracy and time efficiency, we thought that those were equally weighted because they're both very important in order to keep the user safe. For the door and window detection, we have identified doors and windows as well as analyzed location of doors and windows. Once again, these are equally weighted as they're both vitally important to identifying exits. And for navigation, we have the detailed direction as well as the accurate position and location. And once again, these are both equally weighted because they're both important to getting the user out of the burning building.
Here we have our functional decomposition for level 1. As you can see, there's going to be 3 inputs. There's going to be the video data and the location and direction data. There's also going to be power. One of our microcontrollers needs to be powered by a 3.6 volt battery, and there will be for the cameras and for our main microcontroller is going to be powered by a 15 amp circuit breaker. It has to be powered within the constraints of the house. So the microcontroller is going to take in, for the Jetson Nano, the microcontroller is going to take in video data, and it'll be able to detect the fire and objects in the house, and it'll be able to recognize this data and just process it. For the ESP32, it'll take in the location and direction, and it'll be able to process that information as well. This will be combined through data fusion and transfer, and it'll be able to create a map system and be able to navigate the users. And it'll come out as tactile and audio feedback through a speaker and a vibration motor.
Here we have our data flow diagram, and this just shows the transfer of data between the components of our system, starting with the depth camera sensor and ending with the voice commands to our user from the wearable device. And we'll talk about this more later on. As you can see here, we have a diagram showing the description of our system. In the top right corner, you can see the depth camera sensor detecting a fire in the room, as well as simultaneously detecting doors and windows, as well as other obstacles in the room. It does this with the use of the Jetson Nano, which is our CPU, that communicates with the ESP32 microcontroller in the wearable device that calculates the location and direction of the user. And then an escape route is then created and sent to the user via voice commands from the wearable device.
So here we have the related theory for the MPU 6050. You can see on the left that it does a calculation for the roll, pitch, and yaw that is given in theta, phi, and psi, and it'll be able to calculate the angles. The main angle, of course, is the yaw because we have to calculate the direction of the user just to know where they are facing. And on the right, we have the calculations for the acceleration. This will be able to tell us when the mover is using and where they are.
And so some related theory for our software. So we're using the TechNet, which is a neural network model architecture. And when training data, these loss functions are needed to account for said loss. So in the first loss function, we have the sum of the differences between the true and predicted object coverage across all the grid squares in the training data sample. And in the second loss function, we have the mean absolute difference for the true predicted corners of the bounding box for the object covered by each grid square. And then CAFE framework is used. It minimizes the weighted sum of values of these loss functions and linearly combines them. And we can show this actually happening in the next slide.
So here we have the DetectNet training and validation. As Vito said, we use the DetectNet object to actually perform the detections. And there's essentially 5 parts specified for the DetectNet architecture. In the top figure, we see the process for the DetectNet training. First, the data layers ingest the training images and labels, and a transformer layer applies online data augmentation. Then a fully convolutional network performs feature extraction and prediction of object classes and bounding boxes per grid square. Then the loss functions, as Vito talked about before, simultaneously measure the error in 2 tasks of predicting the object coverage and object bounding box corners per grid square. The second figure shows the DetectNet architecture during validation. This includes a clustering function that produces the final set of predicted bounding boxes during validation, and a simplified version of the mean average precision metric that is computed to measure the model performance against the validation set. Here we have a flowchart for the general algorithm for the object detection, as well as the window and door and fire detection. It starts with the camera capturing visual data on the live feed. Then the pattern of the visual data is then detected. Then feature extraction happens, and the trained data set is then used to perform the object detection. If the 2 match, then the object is classified, and if not, the process starts over.
So we have our software implementation. We have the Jetson Nano, which uses Linux 4 Tegra based on the Ubuntu 18.04. Jetson Nano was designed for AI applications, and therefore it can be used for object detection, segmentation, motion tracking, speech processing, which are all pretty relevant within our project. Ultimately, we chose to use Python. When we were first coming up with our project and researching it, we had found that Python was widely liked for doing this object detection and things of this nature. We also got recommendations from faculty and colleagues about this. And then we're also using the pipeline-based multimedia framework GStreamer in order to take in this data. On the right, we have an image. We're going to show a demonstration later on, so this will be included in it. But our object detection is detecting 2 people. And at the top, you can see it classifies the person, and it also shows the % confidence at which it believes it is a person. So we have a 98% and 97% confidence displayed right there. And so this will be further explained later on.
For our hardware implementation, we have our circuit diagram for the MPU 6050 to the ESP32. As you can see on the right, we also have a demonstration video coming up, and I'll talk more about that later.
And for the implementation of the vibration motor with the ESP32, as shown here, we have the circuit diagram, which includes the 1000 ohm resistor along with the diode and the transistor, and it's being regulated along with the ESP32 being connected to the circuit. So for our hardware devices, we have our Jetson Nano, and below is the schematic here with all the components and the inputs of the Jetson Nano, along with our technical specifications. Also, we have our implementation here. So we're using it to apply machine learning algorithms to detect the fire and objects, as well as create a mapping system, and it be able essentially to communicate with the wearable device when the system is alerted.
For the hardware of the ESP32, we have the specifications listed. And for the implementation, we wanted to apply location and direction. It's going to be able to connect to the Jetson Nano, and it will be running the electronics for the wearable device.
This is our camera. It is the IMX21983, and the specifications are here with the 8 megapixel and the resolution. And for our implementation, it will be connected to the Jetson Nano, used as a surveillance camera, and essentially help guide the user out. And then for our hardware for the vibration motor, so essentially here is our specifications as well. And it will be implemented through the ESP32, and it will essentially vibrate to alert the user when the emergency is detected, and essentially just be a supplementary just to ensure that the user is alerted.
And we're going to show you our demonstration video for the ESP32 and MPU 6050. As you can see on the left, it has a gyroscope sensor. However I turn it, it shows the angle in the XYZ direction, or the theta, phi, and psi direction, and the accelerometer also shows how fast a person is accelerating in the XYZ direction. That's good. You could go.
So here we have the vibration motor demonstration, and essentially what you see here in the video is the vibration motor turning on for a second, then turning back on, and it's just repeating the movement. And essentially the circuit is just being switched on and off each second, creating this.
And so for our object detection demonstration, we have a camera hooked up to our Jetson Nano, and it's displaying to the monitor. So here I am, I'm in the frame of the camera walking around, and I'm being detected. As I extend my arms, it's able to extend that frame. And when more than one person comes into the frame, it can detect more than one people. We overlap. It accounts for overlapping, and it also accounts for when someone is only in part of the frame. Here's a detection of a water bottle in my hand. We also, have this feature in here, and this shows that we can detect different types of objects, not just people.
Here we have our corrective actions and iterations. This just shows all of our testing and how much we had to redo some tests. Of course, some actions were very more complicated than others, but some were really done very quickly. This is the unit testing for the hardware. Here we are showing the ESP32 to the MPU 6050. This one was a very basic one that we did at the start. We just wanted to get a voltage reading of 3.6 volts to see that the MPU 6050 was working.
Yeah, and unit testing for software. So this is one of our testing documents for the detection with overlapping. And we did 3 different tests with humans overlapping, items in hands, and behind chairs, desks, tables, etc. They all passed.
So here we have our graphical data of the vibration motor, and essentially what you see here is just a square wave showing the circuit reaching 3.3 volts through the ESP32 GPIO pin, and then it's just going back to 0 for each second and then repeating.
Here we have our timeline for all the work that we've completed. We have it on this slide and on the next slide. It just shows all the work that we've completed so far. We are on time for everything, and we're going to go over that for the milestone. But we're doing really good for this project in terms of time. This is our schedule for next semester. We still have to complete the door and window detection and fire detection, just make sure that it's up and running and that it is able to do everything accurately. We had to make it very efficient. And we're going to do this around the time of winter. We still have the Bluetooth connection, the smoke alarm, LiDAR. That'll probably be done towards mid-semester. We also have to do the map system, audio feedback, and data fusion. The map system and data fusion are very complicated and it takes a lot of time. And the PCB board will probably be the last thing, just to make sure that all the wires are working and are connected, and to put it on a circuit diagram.
So as a team, we were able to accomplish a lot this semester. Starting with the hardware team, we were able to successfully implement the gyroscope, the accelerometer, the camera, and the vibration motor. And for the software team, we were able to successfully implement the object detection algorithm, as well as we are in the final stages of both the fire detection and the window and door detection.
So for future works over the break, we will be working as a hardware team, purchasing the remaining parts, doing the testing for each, and then the documentation as well, along with the implementation of the speaker and the PC board design. And then for the spring semester, we'll be completing all hardware system design and the integration of all the components.
Yeah, and software over the winter break is just going to be tuning up and finishing up that fire and exit detection. We have to also get our research and begin implementing the mapping and work towards data fusion, which is going to be the main task for next semester. So our mapping and data fusion is really our main goals.
So here is our resource breakdown, and essentially it's just showing the activity, descriptions, deliverable, the resources as well. I felt like this was really important in our project to include, just because it's easy for us to just see what everyone else is working on, what's left to do, and essentially just like what's the checkpoints that we've been able to complete. So here we have, purchasing the parts, the configuration of the Jetson Nano, and then the camera testing, and also testing of the microcontrollers and connecting everything, as well as the research towards the algorithms, as well as the object detection, and also the fire detection. Here is our list of the parts ordered so far. The Jetson Nano took up most of our budget just because of the shortages right now. So we've collectively agreed as a group that anything over the budget that we would be financially responsible beyond the budget given to us by the department. This is the remaining parts that are necessary for our project that will be ordered over winter break. And here are standards and our ethical issues. So in terms of standards, we're following this SBI standard, the URT, and the Bluetooth. And in terms of ethical issues, we have the privacy, the protecting data, and the surveillance.
Yeah, so kind of quickly, our complex engineering, we demonstrate complex engineering in a variety of fields. So we have electrical engineering, computer engineering, and computer science as our main areas. And then as like subsets of that, we're doing a lot of computer vision, machine learning, deep learning with our neural networks, and image processing. We have to integrate all of this together, and it is, very complex and tedious. And so for risk analysis, in order to mitigate risk, we created 2 sub-teams of EE and CE based on our areas of expertise. So these teams have checks on each other and obviously can go in and help each other whenever needed. But for the most part, they have their areas of expertise and are going to be leading in their respective work. Due to the nature of our project, it is extremely risky. Fire is, of course, a very dangerous element. So we definitely want to make sure that we practice good safety and reliability within our system. And so in conclusion, our project has made very significant progress, and we're going to continue to build upon it next semester. We demonstrated our research analysis and implementation here in this presentation, and we hope you all enjoyed.
And these are our references.
Well done. Yes, go
I
ahead.
was going to say, on behalf of our team, we would like to thank you, Dr. Almanai, for your time and guidance, as well as the department and everyone here for listening. Thank you.
Sure. Thank you for all of you, and well done, Vito, Alicia, Kari, and Charlie. Any question? Yes, go ahead, Dr. Yakos.
Yeah, it's very fancy project, interesting. I have few questions, 2 questions. Okay, number 1, why you want to use machine learning? Can you explain me, please?
Yeah, so we want to use machine learning because what we're doing is we're taking in a lot of data, and the machine needs to be able to process this data and learn from it so that it can actually map out an area, detect this area, and then guide the BVI user to a safe exit.
Well. In real-time applications, machine learning, you're using this device under which conditions? Outside, outdoor, or indoors?
So this is mainly for indoors.
Okay. So you're going to use for indoors. So you're going to see if you have basically, if you detect fire, if you detect an object, so these are the main, and vibrations, correct or no? So taking one component separately, it's difficult to understand why somebody should use machine learning, number 1. Even if you have a lot of data, since you're doing real-time measurements.
Yes.
So it's difficult to understand, to distinguish fire from not fire. to distinguish objects from not object. Machine learning is useful if you want to distinguish different objects. It's different story. If you want to see different fires, it's different objects. So you have to clarify, I said at the beginning, the apply scenarios, how you're going to apply your design. Now coming to number 2, how you're going to, and the actual distance is very important. You're going to use a LiDAR. What distances are you going to involve to calculate, to estimate the object location using a LiDAR? What's the operating distance?
Yeah, so for the LiDAR, we actually haven't gotten the LiDAR piece yet.
Yeah,
we're going to
you
be
have to
working-
be careful. You have to be careful with the errors. Okay, you have to do first, it's pretty straightforward to do an error analysis for the distance you want to look. You don't want to use meters to go meters far away. Now, so write down error analysis using the LiDAR is very important. Assessment of the machine learning, as I told you, if you're going to use it, is very important. Now, fire detection, how you're going to detect fire? You're using a camera?
Yeah, so right now we're working on using that camera to detect the fire. Yes.
So you're going to use a flames, basically, correct? You're going to detect
Yeah,
flames.
so flames, and
Yeah.
also flames is the main thing. The area around the flames obviously is going to have different pixels, but we're also going to take into account smoke.
Okay, camera cannot detect the smoke. Okay, I understand. I see your point. If this is the case, you can use a very inexpensive UV sensor, 5-10 cents UV, because the flame is very strong emitter of UV light. So having this UV sensor, which is 5-10 cents, you can detect the flame right away. Just, you may want to look that, and this is very efficient. Okay, so consider, as I say earlier, all the physics and the applied scenarios, the usefulness of your techniques. If you want to discriminate different objects, you apply machine learning or different flames. Otherwise, you make it straightforward and you move to the data fusion, which is very important, data fusion. So, and calculate the errors. What errors are expected? For this reason, I ask you the operating distance. Okay. A nice project. I like
Thank
it.
you very much,
Thank you
Dr.
very much.
I appreciate your input.
Thank
Professor,
you.
I have.
Thank you.
What was the name of the sensor that you mentioned again?
UV, a UV sensor costs 5-10 cents. It's like LED. It's like a small LED. Costs 5-10 cents.
All right, thank you,
It's
Professor.
like
We'll look into that.
LED iron. Okay, so look to that. Okay,
Thank you,
very
Dr.
nice
Marcos.
work. Very nice work. I see integration in the project. I like it a lot. And thanks to you and thanks to your advisor. Okay.
Thank you
Okay,
so much,
nothing
Dr. Yakos, for your advice and feedback. Alicia, take the notes to make sure that you implement what Dr. Yakos suggested.
Absolutely.
We're moving to the next presentation.